Hello, and thank you for joining us. Today's webinar topic is part 3 of our Choosing Your GC Column series, presented by Amy Nutter, Technical Product Specialist, and our guest speaker from ResTech, Chris English. This webinar is being recorded and will be available within a few days. If you have any questions, please feel free to submit your questions during the presentation or email Amy and she will follow up with you after the webinar. Now I'm going to turn it over to our presenter, Amy Nutter.
Thank you for the intro. Like she said, I'm Amy Nutter, Technical Product Specialist for the Purge and Trap product line here at Teledyne Tekmar. And today we have Chris English, Laboratory Manager at ResTech Corporation, to give us some tips on troubleshooting our systems from the Purge and Trap all the way to mass spec. So I will cover a quick overview of the Purge and Trap technique and our products, and Chris will give you an overview of part 1 and 2 of our series, which is how to choose the correct GC column for your volatiles analysis and method development. Then he will go over various troubleshooting topics, including how to determine why your compounds might have low or no response, why you're seeing ghost peaks and what causes them, how to deal with contamination, and some compound-specific problems. Then he will tie it all together at the end. So be sure to submit any questions that you have, and we will be able to answer you by email. Now let's get into how Purge and Trap works. The theory of purging and sweeping the sample with an inert gas, called dynamic headspace theory. It sounds simple, but it is a very complex process. Purging a sample to extract analytes is a gas extraction. In purging a sample, the system is no longer at equilibrium. This is because the VOCs that move into the gaseous phase are constantly being removed by the purge gas. Continuously replacing that headspace causes a disequilibrium in that there is always a higher concentration of VOCs in the liquid phase than in the gaseous phase, creating a net movement of VOCs from liquid to gas, extracting the VOCs from the sample more efficiently and improving sensitivity. Then the gas is swept away onto the trap where it has been concentrated and released to the GC. So a basic purge and trap consists of 5 main parts: sparger, flow control, 6-port valve, analytical trap, and heated transfer line. So the sparger is that glassware on the front of the instrument that receives the liquid sample to be purged. And like I said before, purging that sample extracts the VOCs by dispersing inert gas through the sample matrix for a preset time and flow. This flow is controlled by a mass flow controller or a pressure regulator that monitors and precisely controls the gas flow rates throughout the entire purge and trap process. From there, the 6-port valve directs the gas containing the analytes to the analytical trap for concentration. By backflushing carrier gas through the analytical trap, the 6-port valve directs the VOCs to the GC for separation and detection. The analytical trap is used to capture and release VOCs swept out of the sample by the purge gas. Trapping the VOCs creates a smaller band of analytes traveling to the GC column, greater signal-to-noise ratios, lower area-to-height ratios, overall generating sharper peaks and better sensitivity and resolution. So once the VOCs are captured, the trap is heated, causing the VOCs to desorb, and carrier gas is used to desorb VOCs off the analytical trap and carry them through the heated transfer line to the GC. Teledyne Tekmar is the market leader for purge and traps in the US, and we offer several different options. The Lumen Purge and Trap Concentrator, shown on your right, is our standalone waters-only concentrator and can be paired with the Aquatech LVA auto sampler. We also have the combined auto sampler Purge and Trap concentrator, the Atomics XYZ, shown on your left, capable of analyzing soils, solids, and water samples. And we also manufacture other elemental analyzers as well. So now that I've given you a brief introduction to what happens to the sample before it gets to the GC, let's turn it over to our guest speaker, Chris English, who's the laboratory manager at ResTech Corporation. He has managed a team of chemists in ResTech's Innovations Laboratory since 2004. And before taking the reins of the laboratory, he spent 7 years as an environmental chemist and was critical to the development of ResTech's current line of volatile GC columns. Chris will help us to isolate system components from the auto sampler on the Persian trap all the way to the mass spec in order to resolve common problems that might occur during volatiles analysis. It's a pleasure to have you for this series, so go ahead and take it away.
All right, thank you, Amy. I appreciate it. So first, let's do a little overview of where we've come from the last few webinars that we've done, starting with part one, finding the right phase. And we talked about, going out there and finding conditions that are already available. So especially for established methods like EPA 8260 and 524, those types of methods have optimized chromatograms that you can find. So, and Tekmar has optimized chromatograms. And if you're looking at a shorter list, or you want to change column dimensions, that would be a time where you could take a method development, you could look at method development software, whether that's ProEasyGC software, where you can choose your compounds, or a method translation software, where you can translate from one platform to another. If we're looking at different stationary phases, there are a variety of different phases out there that are appropriate for volatiles analysis. There are specific phases that have been designed for these methods, but then there are also very stable phases, like if you're looking at something like a 502.2 type stationary phase, that has diphenyl in it, and that has a long lifetime and can handle higher temperatures. If you're looking at drinking waters, you might be using a VMS type column or a Vocal or a variety of other columns. But the idea of the stationary phase is like dissolves like. So you want to find a stationary phase that's a good match for your target compounds. So for instance, if we're looking at aromatics or TPH, total petroleum hydrocarbon analysis, an appropriate phase would be the 502 type column because it has phenyl in it. And so that's an easy way to remember that. And of course, on your column configurations, we can change those column configurations and maintain the same elution temperature. And the idea with maintaining the same elution temperature on a different column format means that you're going to have similar resolution between compounds. So you can basically translate one column platform to another just using the method translator. So an overview on part two, we go into depth on the method translator, where we can look at a 60-meter column versus a 30-meter column versus, and if that's a 60-meter 0.25 millimeter ID with a 1.4 diameter film thickness, we could translate that into a 30-meter by 0.25 millimeter by 1.4 diameter film thickness. Or we could go as extreme as go from a 60 meter 2.5 1.4 down to a 20 meter 0.18 millimeter ID by 1 diameter film thickness. So there's a whole variety of different translations you can do. The most important translation that we now see is looking at different carrier gases. So whether it's nitrogen or hydrogen, there's a lot of interest now moving from not only hydrogen, but also evaluating nitrogen. And if that's on a mass spec, that's currently hasn't been proven for a list like 8260. But there's certainly some interest in evaluating that. Now, the key to doing a translation to another carrier gas when you're using mass spec is to decrease the flows. You really want 0.5 milliminute or less if you are using hydrogen or another carrier gas other than helium. And the idea behind that is we don't want to increase the source pressure on the mass spectrometer, because therefore we're going to lose sensitivity and have a lot of noise in the background from the electron multiplier. So we talked a little bit about ProEasyGC. ProEasyGC gives you the opportunity to enter whatever compounds you have. We have a database of thousands and thousands of compounds that have been entered on 23 different stationary phases that allow you to enter the compounds, and it will choose the best column and conditions for that specific set of compounds. Every time you enter in a different compound or a different set of compounds, it may recommend an entirely different column. So that's another way that if you're not operating just a standard 8260 524 type method, and you have a subset where you want to look at trihalomethanes and a couple other compounds, you could enter those in there, and you may get a much better column recommendation than you would just using an off-the-shelf column. So this is a powerful tool that can really help to jumpstart your method development. So, and we talked about that. We're choosing your specific compounds, and that's where ProEasyGC comes in. So purge and trap, just to give you a little bit of an overview, our goal is really to remove those volatiles from our 5 mils or our 25 mils of water, and remove those from the water. So we're basically doing an extraction and putting those onto a packing material, so onto a trap. And desorb is really a function of our column dimensions. So if we were, operating a large bore column, our flows would be a lot lower. As we operate a smaller bore column, we generally go with a higher split. That higher split will give us a good signal to noise ratio and a very efficient sample transfer from the trap to the column. And the more efficiently we can transfer that sample, the sharper our analytes are. So that's kind of critical in optimizing your purge and trap. On a 0.25 millimeter ID type column, you're looking at a 20-to-1 split all the way up to a 50-to-1 split. If you're down at a 0.18 or 0.15 column, you could be all the way up to a 100-to-1 split on that system. So, and so we're, this is all a dynamic type extraction. So for the purge analysis, here we're stripping those volatiles out of, in this case, our 5 mils of water in the purge vessel. And those typical flows are going to be 40 mils a minute is generally what we set them at. It's interesting because you can see things like bromoform drop out at ambient temperatures as you drop below 40 mils a minute. So it is critical to set those flows correctly and monitor those flows. A lot of method specific requirements have you at 10 minutes. And you will notice if you're purging, again, at ambient, you'll lose the hexchlorobutadiene and naphthalene, some of those heavier compounds, if you're not purging for a long enough time. So our dry purge, interesting thing with dry purge is if we're looking at materials where water is not going to absorb very well, like our carbon materials. So for instance, like that Vocarb 3000 that has Carbopac and Carboxyn, they're all carbon type materials. We can do an effective dry purge. However, if we're using something like silica gel, dry purge is not going to work at all because that has a high affinity for water. So it's very hydrophilic. So those hydrophobic materials, we can use a dry purge. I've found that a 1 minute dry purge is more decoration than anything else because it doesn't do much. You generally have to go with a longer dry purge. 2 to 4 minutes would be more appropriate than what we have on here, to the 1 to 4. So a desorb preheat, there is no flow, and our goal is to get those compounds off of that adsorbent material so that they're readily desorbed. And what you'll find is less peak distortion, so you get a sharper peak with the desorb, and that's generally about 5 degrees below the desorb temp. And then of course desorb is a back flush, so we're going in the opposite direction. And we'll look at the anatomy of a trap and show the different layers and the reason why we do a back flush on there. Desorbs can be anywhere from 2 to 4 minutes. Generally 2 minutes at the correct temperature works just fine. And then on bake, so bake, the nice part with the Tekmar purge and traps is you can adjust the flow on the bake, and so you can minimize your bake times. So that allows you a much faster cycle time on here. So some of the requirements of a trap, really what we want the trap to do is everything. Like that's how I kind of summarize it. You know, we want the trap to be able to retain, you know, over 100 compounds of interest and not saturate. We don't want any breakthrough. We don't want a lot of CO2 to be collected. So if our carboxin is too adsorbent, we'll pick up too much CO2 and we'll get this big CO2 front. Peak at the front, and then we want it to trap all this stuff, but then we want it to release it too very efficiently. So it is a really tall order for a trap to be able to do all of these things and not absorb water too much, because then we get too much water in the system, and no breakdown as well. So the fact that the industry has been able to come up with materials that work this well is pretty impressive. So this is what a trap looks like, and we're looking at the top of the trap with the high boilers. So we have a less adsorbent material, and then as we go down, we increase in our levels of adsorbency. So we'll see our gases will be down in the carboxin area, and that's kind of the first thing we'll see is the gas breakdown. Chloroethane is one of the first ones that's going to break through on a trap. And you'll see issues with linearity with that compound before any of the other compounds. High boilers, we want those to adsorb and be able to be desorbed. And so they're not going to fall too far down on the trap. And then of course, when we talked about bake, we're now driving any contamination further down into the bed so that it doesn't come off. And eventually what that's going to do is cause your trap to be saturated, and it will no longer work. And of course, we talked about the breakthrough of the gases would be the first thing that you would notice on that. Or you might see some carryover, which we'll get to talk about later in the talk. So some of the common types of traps here, and of course we see dry purge on here. And again, we talked a little about the dry purge. If you see silica gel in there, you're not going to be able to dry purge that. And we have temperature maximums. These temperature maximums can be different depending upon the instrumentation. Some instruments run a little hotter, and that's resistively heated traps that are directly resistively heated tend to run a little hotter than ones that have a sleeve and then have a heating coil that goes around them. So for GC-MS interface, this is really one of the best ways to set it up. Agilent also has a direct line that goes in, and I've seen that that's been effective too. So I've seen minimal dead volume on that, which means that you have good peak shape. This is the easiest way to do it, where we just plumb it into the return line, and then our feed line, we connect it. The thing that you don't see on here is that that fitting there must be covered and kept warm, because that's considered a cold spot right there on that return line, right where you see it says return line. What we generally do is we take fused silica wool, wrap it around that section, and then take foil and wrap it around, and then it's okay to run your temperature, your injection port temperature of 250 or 280. So you can even run it hotter than that if you suspect that you've got issues with that cold spot there. Now, what are we looking for when we see a cold spot? You're going to see a loss in naphthalene response. So the naphthalene is generally the first compound that's going to condense on there. And if it condenses for too long, you'll start to see bleed that's associated with that as it's slowly desorbing off of that site there. So those are some things to look for, but it's an easy way to plumb that in to your system, and it works very well. And it, also you'll actually be able to see leaks from that if the EPC can't maintain pressure. So that's one other little troubleshooting thing that you'll see with on a 7890. The EPCs are so sensitive that if there's a leak, it will go up and down in pressure, and you can suspect it's probably somewhere. The first place to look would be the injection port. So we do have direct on column as well, but that's less common. That's much less common, and also you are more prone to dead volume with that. This allows us to do a split in the inlet, and we can adjust that split with the software quite easily. So for troubleshooting, we want to isolate the different system components. So we'll isolate the instrument first when we don't have any response. And there are a whole variety of things. Like if we see peak tailing, that can be many different factors. Now, if we see peak fronting, we're overloading the column. So it's relatively easy to troubleshoot an overloading of the column by adjusting your split, adjusting your concentration, or sometimes you have to live with it because a fronting peak can be linear in a calibration curve. So it's not actually the end of the world if your top point has a little bit of fronting to it. If you integrate it, it's still going to work. And sometimes we do that to get a larger linear dynamic range. So ghost peaks are something that are difficult to troubleshoot, and yet we have a lot of different ways and tools to figure out what they are. And if we've got a mass spectrometer, that's going to give us a lot of clues to exactly where those ghost peaks are coming from. So in this case, we're going to be troubleshooting a low or no response. So the first thing we want to do is isolate that GC. So we'll perform a direct injection into the GC inlet. And if we receive a signal, now we have to troubleshoot the purge and trap system. So we can check our purge and desorb gas flows. We can check our temperatures, make sure that we've got our temperatures correctly, or that our system is actually heating up. I mean, I had that happen once. I don't know if anyone else has ever had it happen, but I had a trap that wasn't heating up. And of course, I couldn't figure it out. So someone else came in and figured it out very quickly, which was a little bit embarrassing because it just wasn't even something that I even thought about. I was like, they're just somehow the compounds are disappearing into thin air. We purge them and then they vanish, So wrong type of trap, like that happens because I have a whole box full of traps in the drawer, and I'm not careful in looking at the stamp on them. So we end up writing keeping them in their cases and throwing away the old traps too, because that's another thing. We'd suspect a trap is bad and stick it back in the drawer, and then we end up pulling it out again. So repeating the same mistake. So those are some things that you can look at. So we have low or no response. We're troubleshooting the purge and trap. We can run that through. It's nice to be able to step through those cycles, and so therefore you can isolate things from there. And if it's on the auto sampler, there are times where you'll have one position, depending upon what type of auto sampler you have. So, and then we can do a direct run if you've got a two-part system. Like if you had the lumen and then the auto sampler attached to that, then you could separate the two and troubleshoot those. So on low or no response, we're going to do the leak detection. The nice part is whether it's you do want to make sure that your EPC is stable. Generally, you would already probably know that, but also you've got the software system that can do a leak check. And that's a very reliable way to check for leaks. If you have an old style, you can do an old leak type check where you pressurize the system. Nice part is pressurizing the system, whether it's the inlet or the purge and trap, is a great way to exaggerate where the leak is and quickly find it with a leak detector. So on the GC system, we do our direct injection and we don't receive a signal. So, I had another embarrassing situation where the column had broken. And I'm trying to figure out, and of course someone opened the oven door and said, well, it looks like your column is broken. The interesting part is if it breaks somewhere in the middle, like you don't see the break readily. But you have no signal. It's far enough upstream that it didn't shut the mass spec down, because if it's too close to the vacuum, it's going to shut the mass spec down. So, you know, that's one thing. Again, it's probably rare, but another thing to check for, you know, did the column break somewhere along in the coil? So we're checking power signal cables, all that standard stuff, and our carrier gas flow. And we can switch on the mass spec and make sure that we actually have the filament that's operational. So there's a variety of things to do, but you know, sometimes you have to check for the simple things like, is my column even, you know, do I even have column flow? And source pressure is another way that you could see that too on the mass spec. And of course, if the mass spec's not even turning on, you know, that's one thing you could look at. And so ghost peaks, this is a great chromatogram because I think anyone who's run purge and trap for a long period of time has probably seen it, and for a variety of different reasons, right? So we have, it's interesting because we'll have a ghost peak that shows up at that 4 minutes in part A, and then in the next run, it's down at 15 minutes, and then we have another one coming through. And so generally what that is, it's a very high molecular weight contamination that's slowly desorbing out of either the transfer line or the injection port and is now bleeding onto the column. And our column temperature is not hot enough to cook it off. So when we're only going to 220 degrees, it just keeps showing up in the next one. We did a whole series of drum waste samples for a Superfund site once, and we saw a lot of this, and it was identifying as indene, which is a high molecular weight aliphatic type compound that was coming out. And so that's something you can look for. Now, with ghost peaks, you can have siloxanes, and that's your septum. You can have also you can have the Viton O-ring, and that's mass to charge 277. It's triphenylphosphine that comes out, and so that's another thing that you can look for. Impurities in the gas supply, so you want to make sure that you've got your filters on there to remove any impurities that are coming through. And I've talked to many labs where they said, I buy super pure helium, so I don't need filters. And that is just simply not true, especially given that with purge and trap, we are purging a large amount of helium and then putting that on a trap. So we are concentrating any impurities and then they're getting desorbed. So that's a whole nother thing to look for. And then we talked earlier about those cold spots with naphthalene. That can occur anywhere along the way. Trap breakdown, much less common, but if you're using TCLP samples, that can cause trap breakdown, as well as a variety of other issues, not to mention activity in the transfer line. So if you're dealing with the acetic acid TCLP extracts. So troubleshooting compound-specific problems, bromoform's a difficult one, right? Because it's active, but it also doesn't purge well either. So we have low bromoform response. We don't know exactly what's causing it because we could have activity in the transfer line, less likely in the injection port, or we could have our purge conditions aren't set correctly. Bromomethane is another one of those compounds where we could have interference with the methanol that we're not scanning for, but it's there. So it can suppress the signal depending upon our stationary phase, and also to a lesser extent activity. 2-chlorolethylvinyl ether is a reactive compound. It's generally, if you're buying the Megamix standard or you're buying a analytical reference material, it's going to be separate because of its activity, and it doesn't play well with other compounds, so it will break down when it is in a mix with others. And then our 111 TCA, that's transfer line breakdown, and also with 1122, tetrachloroethane is thermal instability, and we can look at that response relative to chlorobenzene and monitor that. So you'll see a significant drop. If it's 50% of chlorobenzene, then we already know that there is an issue somewhere. Ketones, so ketones can be water. You know, we have on their moisture control system, but many times they go hand in hand with moisture, or if we have a cold spot, we can have some moisture condensation there, and that's going to cause the acetone to drop out immediately, as well as the MEK response will drop as well. That's something to look for. Styrene is photosensitive. Unless you have your purging trap in the sunlight, you're probably not going to have to worry about that. But again, you do want amber vials when it's stored and things like that. It's interesting because we did have a purging trap in the sun. So that's why I put that one on there. It's kind of, you know, kind of a funny story. But somebody else, an organic chemist, walked in and figured it out, which is kind of interesting. And then naphthalene. So naphthalene, we say volatility, but it's also those cold spots is one thing. So troubleshooting the mass spec, we're doing our air water check. We want that to be below 5% for nitrogen and our nitrogen and water. So it's basically our air water check, and that's 28 and 18. We can use methanol and scan for 31, but generally that takes a little bit of time. So if we're looking at the interface, that is where the column goes into the mass spectrometer, we can scan for 31, but because it's so hot, the response of 31 is pretty low. So, but that is one way you can do it. And then the other one would be to use dust off and scan for mass to charge 51 and 65. And of course, we're also looking at the mass spec source pressure. The nice part with having a mass spec on there is that it does give us a great opportunity to troubleshoot the system and find leaks more effectively. If you're looking for leaks further upstream, there's a very large time lag if you're going to use the mass spec. So it's whatever the dead time of the column is. So you might be waiting 2 minutes just to see a slug of methanol go through. And if you're anything like me, you're going to put a little methanol on there and stare at the screen for a minute and then get up and walk away. And so it's much better to use a leak detector because that's going to be under pressure. That part of your system is under pressure and you're able to do a troubleshooting that way and see that leak. So troubleshooting contamination, we're looking at silicone. So silicone's mass charge 73, septum is also mass to charge 73. And if we're looking at our column is going to be mass charge 207. They are very similar compounds, but their structures are different. So silicone is very large cyclics, and column bleed is very small cyclics of SiO groups. So we'll have 3 SiO groups for column bleed, and we'll have 7, 8, 9, 10, and above for silicone. Now the mass spec doesn't scan high enough to see the full molecular weight ion. However, you're going to see that 73 fragmentation that occurs. So less common are these vacuum pump oils that you'll see, but when you see them, you'll know something is not right because it's a huge span of different fragmentation, spanning from 55 through 57, 61 through 67. You'll see those on there. And then again, less common again is diffusion pump as well, since there are very few diffusion pumps out there now. And plasticizers, very easy to identify the phthalates because of that distinctive 149 mass to charge ion. So that's kind of an easy one to figure out. So pulling it all together, we want to isolate the problem. However you want to attack that problem, you want to isolate it. I generally write everything down, what I've done, and then that way, if I'm still having issues, I go see someone else and say, hey, can you take a quick look at this? And in my instance, where I was troubleshooting everything, and I went and they opened the oven door and said, yeah, your column's broken. Oh, wait a minute. Yeah, that's not on my notes. I didn't look at that. So it's always good to bounce ideas off your colleagues. Or call tech service. So you can call Tekmar Tech Service or another tech service for help. So, and look at those compounds. Look at the response for all your compounds and look for clues from that. So you know what those, you know which ones are active, you know which ones are cold spots. So those are all, you know which compounds cause breakthrough. Those are all compounds that will give you clues to where the problem is. So, and like we said, document that troubleshooting, because if you document it, then you can just walk over to your colleague or call tech service and kind of go down the list. This is all the stuff I tried. The one thing I didn't look at was opening the oven door and seeing that the column was broken or whatever. So that concludes this part of the troubleshooting, and feel free to reach out to any one of us for help, and we'll be more than happy to help you out.
Yeah, that was great. Thank you so much to Chris for joining us for this series. I know I learned a lot, so I really hope that it helped out our customers too. So please check out our website for all of our latest application notes, including US EPA methods using these ResTech BMS columns. You can view our past webinars, including the webinars earlier on in this series, and listen to our podcast. And you can also visit our online store and follow us on social media too. So thank you, and feel free to submit those questions, and we'll get back to you as soon as we can. Thanks. Have a great day.